talk about a subject that in fact came from engineering. It is, of course, a mathematical problem, but I started working on this because of a proposal of Jaime Moreno, and he's an engineer from Mexico. He works also at UNAM. And so I will present some results for the heat equation that were done with Jaime Moreno and Cristian Montoya, and for the wave equations that was done with one of my students, Alberto Peña. So I will talk about the problem first to introduce the notions I am talking about for ordinary differential equations. So it's just introductory. Okay, so if you have some linear finite dimensional system, so you have an ODE x dot equal to AX with a matrix, and you may have a control there, but in fact, this is not important for our objective, okay? And you have some observations on your system. So this part is important. So you are measuring, you have some answer to your control or your input given by Y. So this is the part you know. So you want, in some sense, to see if your system is working correctly. So what you want to do is to estimate online the real value of your solution, at least asymptotically. So what you want to do is to see if you can modify or you can copy your system, produce it in the computer, and follow your real system. So it's a plane that is flying, and you want to know if something is going wrong with the plane, okay? So you want to do a simulation of the flight with your computer and to see if something is wrong. That's the idea, okay? So you have these results that came from controllability. So if you have some observability results, you know that you can observe the system. But in fact, what we are doing is to construct this copy of the system, maybe something different, but at least you want to do some copy of the system and to estimate the error, okay? So here is a copy of the system and you want to estimate the error. So in fact, if you know A, B, C, the initial data, this error is 0 because you know everything. But in practice, you have a lot of perturbation to the system. So even if you know A and B and C, you really don't know the real initial data, okay? So what you want to do is to work with this copy where you know exactly what you're putting in the system. So you know the initial datum, and you know your control, and you know your observation, and you want the error to decay exponentially to 0. So the idea is to construct this system that may be a copy or not of the original system, and you want to obtain that this error goes to 0 as t goes to infinity. So in general, if A is a Hurwitz matrix, this is the terminology from engineering. So if A has eigenvalues with real part, negative real part, so this is exponentially decaying to 0. Okay, so this depends on the matrix A if you have this copy of the system. But in general, what you are doing is what is called a feedback observer. So in fact, you may construct this matrix L, okay? So this is the construction of your observer. So you have A, you have B, this is given. You have C, this is given, but you want to construct this L that depends on the observations you have, so both in Y and Y hat, and you want to see if the error behave as I told before. It decays exponentially to 0. So the idea is that you are going to estimate the eigenvalues of this new matrix, and then to see if you can give some negative part of the negative real part of this new matrix. So this is new, and then you're going to have a good observer. So in this sense, this is a good observer. So even if you have a matrix that is Hurwitz, so even if you have a matrix that is Hurwitz, you may have some gain on the decay. So you want the system to go faster to 0. Okay, so also, even if A is Hurwitz, you want to see if you can construct L, so it decays faster to 0. Okay, so this is important for the feedback control of dynamical systems, regulation, trajectory tracking, parameter and state estimation. So this is real application. So this is what is happening. Also, the reduction of the sensors you're using. And if something is failing, you want to detect it. And also to modify your control if something is not going as you want. So this is the reasons that we are interested in this kind of problem. There's a problem with the connection from the iPad with the computer, I hope. If not, I switch to the computer, but I prefer the iPad. Okay, so I'm going to talk, so the main part of the talk is to discuss this kind of problems, but in the partial differential equation setting, okay? So the first part is going to talk about the parabolic situation. So we have this semilinear equation, we have a control input U, and you have some measure of your system. This is Y, okay? So this measure may be several things. So for example, you are measuring your solution along a simple curve contained in your domain, or you are measuring it in a subdomain, an open subdomain of omega, or you have a single measurement in the special domain. So you may have or others, okay? So in the previous results that appear in the literature are the case in the one-dimensional setting when you're measuring on a point. So it's like a Dirac delta that appears in your equation. So the only thing you know is your solution at a point x dot, okay? So what they did is using explicit calculations that may be done because it is a one-dimensional setting, they obtain a result. So this is Sean, Moreno, Alvarez, and Neurer, and they get an equation that is like that. So here you have your Dirac delta and another Dirac delta here. And then they are able to construct an observer, okay? So this was done because the particular structure in the one-dimensional setting. So we tried to do it in other setting and it was impossible. So the same techniques were not possible to be done in other settings. So I'm not going to present the results of them because it's much more like doing calculations, but this is the situation they treat in the one-dimensional setting. So with Moreno and Cristian Montoya, we propose a simple situation where the observations were given just by the solution at small set O, okay? So the observer we propose, so I am not taking the original equation, just the observer. So the copy of the system is going to be this one, okay? So the idea, okay, for the heat equation, we know that it decays exponentially. So part of the question we're trying to answer if it is possible to have some gain in this decay, okay? So we want to know if we can make this decay faster, this decay to zero faster, okay? So if you estimate the error, you have this equation that is verified by the error. Of course, if it is semi-linear, you have this difference here that depends on the original equation and on the observer. So this term is due to the observer, and this one is due to the original system. And you will have this term here that is, in fact, that is going to give this gain in the decay. Okay, so to solve this problem, we work with this elliptic equation, and we prove that this A is a generator of a C0 semigroup, and we can get easily that it decays at minus lambda1 plus k dot, where lambda1 is the first eigenvalue of the Dirichlet Laplacian. Of course, this proves that you can have some gain, okay? At least you can choose k dot such that this exponential decay is larger than only lambda1, okay? So you can move your exponential decay is going to be faster. So this is the easy problem we try to solve. So here for the semi-linear case, of course, you can use Poincaré-Lyapunov theorem, and we use the fact that if your semi-linearity is globally Lipschitz, then you can obtain k dots less, such that this term is less than 0, and you obtain your exponential decay. So in this case, it's easy. what happens if you are able to observe your solution along a curve? Okay, well, here things are becoming more difficult, okay, and you will see why. Okay, imagine that you are in a rectangular domain. So we are trying to do something as Moreno, Shawn, and all them, but now in the two-dimensional set. So you have information of your solution only in a line parallel to the rectangle, to the sides of your rectangle. So maybe you can observe all along this line, or maybe all along this line, okay? So this is a natural, more or less, natural way of observe your solution. So the original system, we are trying to work with the linear case, okay? So your observations are, for example, only your solution in this x dot, y, and time, okay? So we propose this kind of observer. So we propose some value, G1, times the sinus of pi x over a. So we are observing here. So here it is related with the eigenfunctions of the Dirichlet Laplacian on the interval 0a, okay? And then the difference between the observation in W, that is the observer we are constructing, and what is observed on the solution of the original system Z, okay? And here you have the same control and an initial data that you put inside, okay? So what I was saying at the beginning is that in general, you don't know precisely your initial data, okay? So you may have some perturbation. So here in your observer, you can choose your initial data, okay? So if you look at the error, you will have that the error is given by this equation, okay? And then you can write the solution in terms of the eigenfunctions of the Dirichlet Laplacian. So you are just writing the solution in its Fourier series, okay? And you have that the eigenvalues of the Fourier, the eigenvalues of the Dirichlet Laplacian in this rectangle are given by these values. And then the eigenfunctions are a multiplication of this sinus with this sinus, okay? So you can write E with its Fourier series, and then E is given in this way. And if you put this expression in the equation, you obtain this equality, okay? So what you can do now is to multiply in the interval 0a by the eigenfunction in the value x, okay? And you see that all these terms are 0 when L is different from 1. Why? Because I put in the observer this sinus, that is the first eigenvalue of the Dirichlet Laplacian, eigenfunction, sorry, of the Dirichlet Laplacian on the interval 0a, okay? So it's orthogonal to all the other eigenfunctions, so to psi m for m different from 1. So then you will get this equal to 0 for L different from 1, okay? And then you can solve this ordinary differential equation, and that's all for that. And then for L equal to 1, you will get, so here L is equal to 1, and then you don't get a right-hand side equal to 0. You get that, okay? That is different from 0. So you can solve this equation, and you obtain that the first component of the error is given by this times plus this other term. So here you have an exponential decay, okay? If you can choose, so this depends on the sign of psi 1 of x dot. So for example, if psi 1 of x dot is equal to 0, you cannot have gain, okay? It's impossible to obtain some gain in the decay. But if psi 1 of c dot is different from 0, it depends on the sign of it, and then you can choose g1, so this is positive, so you will obtain an exponential decay, okay? So in general, it depends on the sign of this value of the eigenfunction of the first eigenfunction at the particular point. So you can try to use more GKs and more eigenvalues, okay? But a finite number. So if you try to do that, you obtain for the first this kind of decay, and then you have to work with the finite modes where you don't have this orthogonality, okay? So as before, you have to work with all the terms that you don't have a 0 there, okay? And then you have to choose to work with this matrix that depends on the values of the eigenfunctions at x dot. And then you have to choose G1, G2, and Gn in such a way that this matrix with this one, adding both, is Hurwitz. So it's like in the ODE case. So sometimes you may work with that and sometimes not. But in general, you can have a gain in the decay if they are not all 0. Okay, so in some cases you can have this gain and you are done. Okay, so we made also some numerical experiments. So we can see that this works, okay, for the observations in these lines that are parallel to the sides of the rectangles. So in fact, in this situation, we have, I am running because we don't have much time, okay? So in this case, we have several open problems for the heat equation. For the case of the observations parallel to the sides of the rectangle, we don't know how to do the semilinear case. So it's an open problem. And what happens if, even in the rectangle situation, you may think that it's interesting to see what happens if you observe along a line that crosses the rectangle, but it's not a line parallel to one of the sides. So this is also an interesting problem, and we don't know what to do. And also, what happens if in R2, for example, you have something that is not a rectangle, and you want to observe along a line that crosses all the domain. So these are open problems in the case of the heat equation. So now I'm going to talk about a similar problem but for the wave equation. So we have our wave equation with our boundary control and some initial data. So you are going to have two observations. So one of the position and one on the velocity. And again, we ask if it is possible to construct an observer that we have the error exponential decaying to 0 as t goes to infinity. So this thing is related to a stabilization, okay, of the wave equation. So we consider an observer design given by something like that. So you have to choose a function g that depends on z and w, that is your observer, but it's related with the observations you had with the original system. So we need to include this information. No? What can you see on the position and the velocity of your wave? Okay, so we can think or try to solve the problem if you observe in a small set the position of the wave, and on the same small set the velocity of the wave. So we propose a function g that is given by that. So here are the observations, and here are the terms that are related with w, the observer you are designing. Okay, so if you do that, we may try to obtain this decay. So I will say that in the one-dimensional setting, there are some results due to Smith, I don't know how to pronounce that, Serpa and Christic, and they prove some results that are similar to the ones I'm going to show you, but they use different techniques. So more techniques that came from engineering, I will say. Okay, so if you see our observation error satisfies this system, okay, so you are going to have this term that is related with the velocity, and this term that is related with the position. Okay, so what we're trying to do to see if you have this decay. So in literature, you can see that this damping is not enough sometimes to get the exponential decay, and you need also something related to the position. because you can have some overdamping. So there are some results that imply the overdamping, and so you cannot have this gain in the decay. Okay, so using some Kahneman estimates and energy estimates, we are going to obtain an explicit exponential rate decay delta that is given by the supremum of delta for every solution of our equation. So we are working in the situation in which the initial data of the position is H10 in this Sobolev space, and the velocity is L2. Okay, so this is the energy. So we will use a very important method introduced by Arrow, where he proved that if you have a subdomain and a time such that this observability inequality is true, then you are going to have an exponential decay of this form. So we are going to use this kind of observability inequality. So yesterday, in the talk of Nicolas Carreño, you heard some things about observability inequality. So this is related to really controllability. Okay, so we need to prove an observability inequality of this way, and this is going to imply this inequality, and here we have precisely the exponential decay. Okay, so the question is if we can have a gain in this exponential decay. Okay, so we have that for every solution of 11, so it decays. So because just multiplying by the E sub t and integrating, you will have that the energy is decreasing. So this is easy to do, and here you don't need an exponential decay. So just to see that it decays. Okay. So if you want to estimate the terms, the energy, let's say in terms of this damping, you can see that you have this decay if you have that. Okay, and under the same assumption, you can show this estimation. So to prove that the observability inequality implies the decay, we have to multiply the solution by the time derivative of the solution, and then just to integrate. And we will get that using the previous results. And then you obtain that the difference of the energy is bounded by this, and this term is positive. So using the lemmas and the inequality, you will prove this. And finally, we will get that the energy at time capital T is less than gamma times the energy at 0, and gamma is precisely less than 1. So you can do all these estimates and you obtain this result. So now the thing is, if it is possible to choose this gamma in a good way, okay, or modify gamma in a good way. So you can estimate using the semi-groove property of the solution of the wave equation, you obtain that the energy at K times capital T is less or equal than gamma to the K times the energy in zero. And if you modify and you write the time as KT plus eta, you obtain this inequality. So this is like now classical way of obtaining this decay. So we get an exponential decay, okay? So is it possible to get a gain in the exponential decay? Well, in general, we don't know. So we have this number, but we cannot obtain the gain from here. So the same happens to this result I mentioned by Serpa and Christik and Schmeider for the one-dimensional setting, okay? They are not able to obtain a gain, so to modify this gamma, even if it depends on A and B that were our parameters in the observation, okay? So we put these parameters A and B in the observer, but we don't know how to modify these parameters, or if it is possible to modify the parameters in order to obtain some gain in the decay in general, okay? So what happens only is if we are observing in the whole domain, okay, but this is only of interest in mathematics, not in practice, because observing everywhere, so you know everything about the solution, so it's not very good, but when you observe everywhere, it is possible to have a gain. In this situation, yes, clearly you can have a gain, and here you have to propose the parameters 2a in front of the derivative and b here, and then you can work with the system just to rewrite it as a matrix, okay, one-dimensional derivative, one derivative in time. So here you can work with your eigenvalues of this wave operator, and you can play with A and B in order to get this negative real part, okay? So in this case, you using an orthogonal basis of the eigenfunctions of the Dirichlet Laplacian, you can see that in fact you can obtain real parts that are negative and are related to A. But as I said before, in this situation, we are having, as observers, everything. We are observing everything. So the position in the whole domain and the velocity in the whole domain. So this is not very good result, but it's something. And okay, so here are the calculations. So if somebody wants to read them, I can send you the paper, but I think it's not very interesting for a conference. Okay, so we have also open problems. So how to construct observers for the wave equation that give some gain and are like more interesting. We have this result where you observe everywhere in the domain. So, okay, and you have this result that may be interesting from the mathematical point of view, but not from the practice point of view. So you're observing everywhere in all my domain omega. So, okay, that's not very good. So we want really try to solve the problem. So you have your wave equation maybe to observe here, no? What do you need to observe there in order to have this exponential domain? So we know these things like it is not enough to observe the y sub t, because you can have over damping. Okay, so we put the y, but can we modify that? In which way can we work with that to have some gain? Is it possible if we are just observing in a part of the domain or on the boundary? Again, we can try to do things observing on the boundary, but not in the whole boundary, just in part of the boundary. No. And of course, the way we work with this equation does not allow to treat the semi-linear situation. So, okay, thank you.